Hello everyone and welcome to ANTS 2020 in Digital Auckland. My name is Novak Kaluderovic and I'll be presenting the paper titled Cryptanalysis of the Generalized Legendre Pseudorandom Function. This is joint work with Thorsten Kleinjung and Dusan Kostic from EPFL. So, what is the Legendre pseudorandom function? Pseudorandom functions are a set of keyed functions with the same domain and the same codomain, such that a function sampled at randomly over a set of keys cannot be distinguished from a truly random function with the same domain and the same codomain. Why Legendre? Well, because we'll be using the Legendre symbol. So let B be an odd prime, then the Legendre symbol of x is equal to 1 if x is a square mod p, and -1 if x is not a square mod p. An important property of the Legendre symbol is that it is multiplicative. So the symbol of A times the symbol of B is equal to the symbol of AB. The Legendre pseudorandom function was introduced by Damgaard in 1988, and it was defined as the function that on input x outputs the Legendre symbol of x plus k. In this case, the key is k, which is a value in FP. A generalization was given by Russell and Sperlinski called the generalized Legendre pseudorandom function, which on input x outputs the Legendre symbol of f of x, and f is a monic polynomial of degree r in fp of x. Now we'll give an algorithm that is given access to this oracle OF, and with which we compute the secret key f. So why are we interested in the Legendre pseudorandom functions? To compute one bit of output of this function, we need to compute one Legendre symbol. Now this is relatively slow with respect to other cryptographic primitives, and it was not used in practice until recently. In 2016, Grassi et al. Showed that it's actually very suitable for multi-party computation, and that in that scenario, it is pretty fast pseudorandom function. In 2019, Ethereum showed some plans to incorporate it in their blockchain, and to that goal, they posted a number of online challenges to break this function. We will give an algorithm for breaking it, and we will show how we solved some of these challenges. Now, before we proceed to the algorithm, I need to give a couple more definitions. A Legendre sequence of starting value A and of length L is a sequence of Legendre symbols evaluated at A plus 1, A plus 2, up to A plus L minus 1. Throughout the presentation, we will work with Legendre sequences of a fixed length L, and we will assume that this length is such that the sequences uniquely define their starting point. In other words, two elements have the same sequence if and only if they're equal themselves. There's a generalization of this. So for monic polynomials of degree r, we define their Legendre sequence as the sequence of Legendre symbols of f of 0, f of 1, up to f of l minus 1. And again, we will work with sequences of length l, which uniquely define their polynomials. What is important is that these sequences are logarithmic in p, and we can assume that their length is 2 times r log p. So let's go to the algorithm. The problem is the following. So we're given oracle associated to f, and we want to find polynomial f. What we're going to do is to use a table-based collision search. So we create a table with many Legendre sequences of corresponding polynomials fm, and these polynomials need to have two important properties. So firstly, we can compute the sequence of polynomials fm from the oracle of f. And the second property is that if we find one of these polynomials fm, then from them we can obtain the polynomial f, and we can thus find the secret key. Once we create this table, we go to the search phase, where we essentially generate random polynomials, compute their Legendre sequences, and look for hits in the table. If we find a collision, so those two sequences are equal, then their corresponding polynomials are equal, so we actually found a polynomial fm, and from fm, as we said previously, we will be able to obtain f. So how do we define these polynomials fm? To define them, we will use rational Möbius transformations. So we know these are transformations of P1 that send xy to ax plus by, cx plus dy. And it is well known that the group of rational transformations is isomorphic to PGL2, and elements can be represented as matrices A, B, C, D. And there is a natural action of these matrices to monic polynomials. So matrix M acts on the polynomial f by sending it to the polynomial fm, which we define to be f evaluated at ax plus b divided by cx plus d. There is a slight problem here because this is not a polynomial, it's a rational function. So in order to take care of that, we add the normalizing factor, we multiply everything by cx plus d to the power r to get rid of the denominator. Again, this becomes a polynomial, but not monic, so we divide out the leading coefficient. So now we have given an action that takes a monic polynomial and sends it to another monic polynomial. So in a way, this action permutes the key space of the Legendre pseudorandom functions. So what can we do with these functions fm? They have a very nice form where we actually essentially have product of 4 elements. And we can use that to compute the Legendre symbol of fm from the oracle of f. So in fact, the Legendre symbol of fm evaluated at x can be obtained by querying the oracle at ax plus b over cx plus d, multiplying that by the Legendre symbol of cx plus d raised to the power r, multiplying that further by an oracle query at a over c, and finally multiplying that by the Legendre symbol of c to the power r. So since we can obtain symbols of the polynomial fx, fm, we can obtain the whole sequence, the Legendre sequence of fm. How do we do that? Well, we simply query the oracle L times. So at all these x values going from 0 up to L minus 1, and additional query at A over C, and we compute additional L plus 1 Legendre symbols and multiply all these values. With them, we can obtain the Legendre sequence of fm. So in order to obtain one Legendre sequence for one matrix in PGL2 or one Möbius transformation, we need L oracle queries. However, we can we can lower this cost by considering the amortized cost in queries for obtaining these sequences. So if we query the oracle at all inputs, so the whole FP, then we will be able to obtain actions of the whole Möbius transformation group on the polynomial f. In other words, from P oracle queries, we will obtain a cubic yield in the number of sequences that we can obtain. So from P queries, we get P cube Legendre sequences. This leads us to the algorithm for finding the secret key f. As we said, it's a table-based collision search, and it's pretty straightforward. So there are two phases. In the pre-computation phase, we create a table that contains Legendre sequences of all polynomials fm for all Möbius transformations m. So in total, we create a table with p cube sequences. In the search phase, we sample random polynomials of degree r, compute their corresponding Legendre sequence until we find a hit in the table. And finally, the hit will lead us to the key f. Now we expect to finish the search phase after p to the r minus 3 trials. So the runtime is essentially p cubed for the pre-computation part and p to the r minus 3 for the search part. If r is lower, then we can lower this runtime by simply limiting the table to p to the r over 2, and we can reach the optimal runtime, which is the birthday bound, essentially, for these table-based searches. How many oracle queries do we need in order to create a p cube table? Well, as we said previously, we needed p oracle queries. Now, it's not hard to convince oneself that if we have slightly less queries, we can still obtain somewhere around p of p cube sequences from that. So if you have p minus little o of p over l oracle queries, we can still reach this p cube plus p to the r minus 3 runtime. This, of course, poses a natural question. Okay, but what if we're not allowed to do this many queries? And what if the number of Oracle queries is severely limited? A straightforward example is the linear Legendre PRF. In fact, there we can create a square root of p table with square root of p queries, so we don't need to do any more than that. So the question that we ask ourselves is, if we're given m queries, how many different group actions can we obtain from that? Or in other words, how many Legendre sequences? Now, we do this by considering a subgroup of the Möbius transformation group, which we call the linear shift subgroup. So this is the group of matrices di01, and if we think of them as Möbius transformations, they essentially send x to dx plus I. And we denote with FID the action of such polynomial on the secret polynomial f. We can compute the symbol of FID by querying the oracle at points dx plus I and multiplying that with the Legendre symbol of d. So how would the algorithm look? So we have m queries, and let's suppose we query the oracle at 0, m. So in 0, 1, 2, up to m minus 1. In other words, imagine that we have this interval of oracle queries or of symbols of f of x. And we want to find the Legendre sequence of FID. So in order to obtain it, we need to extract the symbol at position I, the symbol of position d plus I, 2d plus I, and so on, up to L minus 1d plus I. In other words, we need to extract an arithmetic sequence of length L within this interval of 0, m. And how many sequences of these type are contained in 0, m? Somewhere around m squared over L. So from m queries, we can obtain m squared over L Legendre sequences. This gives rise to the following algorithm in the limited query case. So pre-computation, we query the oracle in the interval 0, m, and we create a table with m squared over L sequences. And then in the search phase, we simply compute random polynomials until we find a hit in the table. The expected runtime is p to the r divided by the table size, which is m squared over L. So how do these algorithms compare to the previous best algorithms? The first algorithm was given by Kaluderovic in 2019. Now, in our terminology, their algorithm essentially uses the group G, the linear shift group, with the value D set equal to 1. However, the author gives a memory-less approach, but we can think of the algorithm as a table-based collision search where the table is of size m over L with m queries. An improvement was later given by Bullens et al., where they use, again, in our terminology, the group G with I strictly smaller than D. And this allowed them to create a table of size m squared over L squared. Finally, our algorithm uses the full group G, and with m queries, we can obtain m squared over L Legendre sequences. So an improvement of a factor L. And this is the comparison of the three algorithms. Now, in the general case, so when the number of queries can go up to P, Kaluderovic proposes the same algorithm where essentially their sequence yield from P queries is O of P sequences. Bullens et al., as previously from P queries, obtain around O of P square sequences, and then we show how to exploit the full Möbius transformation group, and from P queries, we show how to obtain P cube sequences. And again, the runtime is always P to the R divided by these table sizes, which are linear, quadratic, and cubic in the third case. Finally, as said previously, Ethereum research posted a number of challenges for breaking this Legendre pseudorandom function. In particular, they posted 5 linear Legendre challenges online for primes varying from 64 up to 148 bits. In all cases, we were given around 1 million of symbols of a long Legendre sequence of a polynomial f, which is linear, so f is x plus k, and the goal was to find the secret polynomial, or equivalently to find the secret value k. In our implementation, we worked with sequences of length 64, and this allowed us to create a table which contained around 2 to the 34 sequences. In the search phase, we did about 2.2 million trials per second, and these are the final results. Now, for the 64-bit prime challenge and the 70-bit prime challenge, they were first solved by the Bullens et al. Team, and we were the first to solve the 84-bit prime challenge. In fact, the main improvement was that factor L larger table, which allowed us essentially to find the hidden key with less trials. The 100-bit challenge is still far from being solved, so our estimates tell us that we need, at least our algorithm has an expected runtime in core hours of 9 billion core hours, and this is still far from being solved. It's still an open question if one could create a cubic yield from a limited query case. So if from M we can obtain M cubed many sequences, and that would probably give a computable solution to the 100-bit prime size. But for the 148-bit challenge, probably a different algorithm is needed. With that, I conclude. Thank you for your attention, and keep safe.